Cool. So now we will discuss about something called um, failures in HDFS. So all the things that we are discussed right now, right? Like we will input a file, or we will like dump a file onto our HDFS file storage system, and then we are good to go, right? And when we want to read the file or when we want to write again, it is happening fine. So these are all called as happy paths, right? Or happy paths in architecture, system design, or in database terms. Happy paths means that suppose you designed a system to do tasks in stages, right? One, two, three, and the systems behave exactly like this. These are called happy paths, right? Because everybody is happy because the machine is performing, as expected, right? These are called happy paths. Now, what if the system doesn't, follow these happy paths? How do we recover, or how do we make sure that we are still performing as expected by the end user of the system, basically our clients, even though our system is not performing, or it is not taking the happy paths all the time. So how does this happen? How does the system not take the happy paths, right? So one thing in our system, this is not like exactly as the terminology that is associated only with Hadoop, but it is like associated with any systems that are complex enough, or designed in distributed manner, especially in distributed manner, right? So how does that work? So we have something called as worker node failures. We have something called as name node failures, and we have something called as block corruption. These are major categories. There are n number of things, like where the operating system on nodes will just act up and fail. We have hard drive failures, where the hard drives on these systems will just end up just giving up because they have been operational like 24 hours a day, 7 days a week. And we have something like application failures, like where the how the system is tracking these block corruption, all of this, that particular application itself has bugs, right? So we are not discussing all of these, right? We are only discussing about the system failures, the how these systems behave, how these component behave. So when they don't behave well, how does these failures work? How does these failures happen? So we are discussing this. The broader category is these three, right? So anytime you discuss about HDFS, right, the failures in HDFS or the not so happy parts, we will discuss about these three stuff, right? So what's a worker node failure? Anyone can just throw in some light. I'll explain. I'll top it off that. Anyone wants to do it? Okay, thumbs up, thumbs down. Somebody, man, somebody just speak. Yeah, no issues. So here, what happens here is that generally when we take about a distributed system, right, the chance of failure of a system will be almost a common occurrence. What do I mean by that? Suppose we have one system, one node, right? One node, just one node, right? The chance of this node going down will be, let's say, one time a day, right? Or even 5 times a day, right? 5 times a day. So this is my chance of the system going down, like one node. But if you have 1,000 nodes, right? So even if one node goes down one time a day, that means we have 1,000 failures here, right? 1,000 failures here of node failures, just node failures, right? Let's say these are worker nodes. Okay. So that means 1,000 failures means divided by 24, right? 1,000 divided by 24. Somebody, who is handy. This is 500. This is, 12. This is 6. This is 250. And this is 3. This is, something like 125. 125 divided by 4, something like, 18 failures per minute, or, something like that, right? Per hour, basically. So there are 18 failures, or like three, four, sorry, not, mm,
I think
okay,
around 40.
yeah, around 40. Thank you, guys. Around 40 failures an hour, right? Around 40 failures an hour. That is really, really, really high, right? This is a 1,000 node cluster. Why I'm taking 1,000 node cluster? Because when Google like released the white paper first, they said that we are using at least a 1,000 node cluster, and failures in these nodes are pretty common to us. Even if we like take a napkin math, right? Like just on the back of my envelope, I just calculated something here. It is 40 failures a minute, sorry, 40 failures an hour. This is extremely high, right? How does our infrastructure still keep up if we are having 40 failures every hour? Because as I said, right, as soon as we have any failure, the nodes, and the name node, the master node, and the nodes here has to adjust. If we have infrastructure lying around, we can always have a copy available here, right? A new copy of the node available here. If we have a nodes lying around, we can again we have to like copy all the nodes that are failed here from different nodes. Sorry, copy all the blocks from the failed node here, right? It takes a lot of time. How is our name node keeping up, right? How is our naming node keeping up for this one, trying to keep the replicas up? Because we told that at any given point in time we have three copies of data, 3x data, right? Let's say we have terabyte of data. That means we are having 3 terabytes of data across blocks, across machines, all the time. So the node, the name node, and the like data nodes has to maintain the data three times all the time, every single day, 24 hours of a time, withstanding around 40 failures every minute per 1,000 node cluster, right? So this is a good challenge to have. Why does these failures happen? Why does this failures happen? Because we are using commodity hardware in the first place. Commodity hardware means you know I am ripping out my desktop now, and literally like plugging it plugging the hard drive, motherboard, jamming it into one place, and then saying that okay, this is one system now. I will, take out, my friends, like desktop again. I'll connect both of these through network. So this becomes my cluster. That's how Google did it. And, that's how the hardware reliability was at that time when Google did it, right? So now when we said some principles, right, when we are guaranteeing that, okay, I am, keeping my, like replication factor 3 all the time. This is the guarantee that this system provided us when we, wanted to explore, right? When we wanted to find an alternative to the systems that were previous to it, the like the MPP databases, the old school data warehouses. We said that we are going to like increase the availability of our data, and we will not have any downtime. We can ingest lots and lots of data because we can scale, right? We can scale the data as and when we want, right? So this like promise comes with lot of challenges. That one of the challenges are data node failures, right? So how does this do? As soon as some we have decided to like give all of these, right, promises, right? How does this happen? How does the failure, how do we keep up with the failures? The first thing is, we will keep up with the heartbeats. So every 3 seconds, my node will communicate to name node saying that, okay, I am alive, I am awake, and my data is fine. Okay. This is one of the mechanisms to mitigate the errors. If the data node goes down and it doesn't communicate to name node, right? Then it's a huge problem, right? It's a huge disaster because the client that is sitting here will never bother about whether your data node goes down or whether your name node acts up, right? He wants his data. He can be a data engineer, okay? He can be a ML engineer, he can be a data analyst, or he can be just a business user, right? They don't care about all the complexity that you are going through. All they want is just the data. We said that Hadoop is scalable system and it can deliver us data in time. So they expect the data to be here. So how do we ensure that our cluster is up? Okay, this is a technical challenge for us data engineers, right? So we said that okay, we will have 3 second heartbeats. Okay, every time, every 3 seconds, I'll say that okay, I am sending a report here saying that okay, I'm fine, my data is fine, because it's not just the data node. I have to get the data from my hard drive here, saying that okay, none of the data in my hard drive is corrupted. So that is where this one goes. So what if the name node doesn't answer every 3 seconds? Sorry, the data node doesn't answer every 3 seconds, right? Roughly 3 seconds or 5 seconds, right? The name node constantly pings it after every 3 seconds, and it waits till 10 minutes, around roughly 10 minutes, right? This 10 minutes is very crucial because the name node can go ahead and bring up a new node here, just to be sure, because it doesn't hurt if we have infrastructure lying around. If it doesn't have, it will try to get the block report as well, within the 10 minutes, right? If the data node answers within 10 minutes, it's fine. It will just check the block reports whether the data is synced, because the name node has this like metadata table lying around. Let's say somebody has updated the block one on a different node, right? That has no issues. The hash or the checksum of this particular node, sorry, block in the different node will be very different, right? So what happens is that okay, the name node identifies that the data for the same block has different checksums. So what it will do is, since the machine comes up after 10 minutes or within 10 minutes, maybe 5 or 6 minutes, some data write operation might have happened. So it will just sync the data back to this node. From if the B3 block 3 is here, the block 3 is updated here, it will sync back. So this ensures that the data is not lagging behind, or we are providing stale data to our clients, right? Any doubts here? Okay, I'll take that as a no. Now, if the name node, sorry, data node, just straight up fails, like after 10 minutes, it didn't, reply as anything, right? It straight up failed. So what happens now? As I told, right, the name node, the data node, as it is not responding even after 10 minutes of his highest threshold, it will make the name node like cognizant of the fact that my replication factor has gone down. Okay, not all blocks of data has replication factor of 3, because we are continuously keeping track of every block and every single data node here, right? The name node knows it. That's the main like agenda of name node here, right? So even if the blocks are not keeping up with the replication factor, even if there are 40 failures every hour, right, we have to keep up with the replication factor within that hour, right? Every single hour, or else we will have data staleness. Our stakeholders will never trust our data, right? So that's a huge problem, right? We as a data engineers want to keep one single source of truth of the data, right? That's our primary business goal of our role. So if we can't keep up with the replication factors, the node failures, right, then the data trust will be gone. So that is our though it is a complex system, it is still able to do all of this, right? Let's suppose it is able to do that. So if some block, gets corrupted, if some block is not available on a node, or the whole node, goes down, right? This is how we are going to like this one. So how does this do? Generally, these, nodes will be stacked up in a server. That means, like, in the previous sessions, we have discussed about the first origins of the Google thing, right? Okay. So if you see here, this one single node here, this one single machine here will be a node, right? This one is a data node. Okay, let me just choose a different color so that I can highlight better, right? This particular machine that you are seeing here, this is one node. It can be a data node, it can be a master node, but this is one node, right? This is this is how these are stacked upon. Whatever you are seeing right here, this is your network controller. Basically, this is how your network from this node to this node happens, right? When we say block replication, right, copying the block from the healthy node to a new node, or the stale node, basically, right? So we have to go through this controller again and say that, okay, my healthy node is here. Okay, this is my healthy node, and this is my new node or the lagging node. So I'll say that, okay, my name node, let's say, for simplicity, my name node is here. It will come to this node and say that, okay, you have to pass this data to here. So it has given this IP address. It has given the which block, the name node will communicate which block to replicate. So that node, will, straight up push the data to the node directly from one node to another node, rather than communicating it through the name node, because name node is, again, like, it has to keep track of all the nodes. It has to keep track of all the communications, metadata of these files, blocks, everything. So it doesn't bother with like data itself. So it will just say that, okay, replicate this block on your machine in this machine at this path. So that's what it does. Okay, and that's how we will be able to like replicate the data in blocks across our nodes, even in case of failures. Am I making sense? Anyone has any doubts or anything flying right off their heads? Okay, so this is how a name node keeps track of data node failures. Okay, this is still better in the term that you know we can we have data replicas flying around all the time, and we can just easily replicate, right? What if our whole name node goes down, like this whole thing just straight up goes down? What happens? Anyone? This is a fun one, by the way, like, really, really, really fun challenge. Anyone? Okay, I take that as a no. Darshan, you want to say something, or you are saying something?
No, no, that's second time.
Okay, cool. So now in Hadoop version 1, right? In Hadoop version 1, when Google released this GFS paper, or Google file system paper, right? They used only one name node. They said that this is fine. Okay, for the operations that we are doing, this is fine. But since this has been tested across companies in Silicon Valley, across internet-based companies, right? They quickly understood that this doesn't cut it. Okay, having one name node, because the primary limitation of name node is that all the metadata that you see here that we have discussed at length, right? The metadata is stored on one single like RAM of one single machine. This is limited by the cluster resource utilization is directly limited by how much of metadata that this particular name node can handle, right, at any given point in time, right? This is a serious issue, and they wanted to address this, but they kind of had the plans, but somehow it's always a bottleneck, basically, right? And when these failures happened, right, the worst thing that was that the restarts were, really painful, because as we discussed earlier, right? We have the file system image, current file system image, but everything that we are inputting in the edit log, had to be synced with our, file system image to create one image, right? And that was called as checkpointing. That checkpointing used to take hours. That checkpointing itself used to take hours, hours on end, because you had millions of files, okay, images, videos, a database, dumps, text files, HTML files, your, audits, all of these things, like literally, dumped on your, HDFS file system, because this is a file system. This can scale anytime. So these are millions and millions and millions of files, the metadata of these files stored in one single server. And that single server, when it failed, gone, right? You have to calculate the file system image. And this, process is called as checkpointing, where we are merging the file system image, the current file system image when the last restart happened, and all the edit logs to create the latest image of the file system. This is always required. Unless this is present, right, we will not be able to perform any actions, because your file system image is basically your map of your cluster, right? If you are in a new city, and this is you, if you don't have a map, right, your Google map or your, physical map on your hand, you can't navigate any city by yourself, because you don't know the language. You don't know how blocks are stored here, right? How blocks are being made here. That is your city, basically. You cannot, like walk into a city, and then, you cannot talk, language to the locals. Even if you do talk to them, they will not, like help you, like, all the time. So you need the map all the time, right? If you can, read the language, if you can, understand, navigate, right? You need the map all the time. So when this Hadoop V1, happened, right? They had only one name node, and then it kind of, created single point of failure. Single point of failures are always a bane of, any system, any distributed system, right? If you have a single point of failure, when we say that, not so happy paths happen, right? It will just bring down the whole system, and everybody who is dependent on the system, like every stakeholder, right? They'll just complain and complain and complain and saying that, okay, your system is useless, basically. So how do we avoid that, right? In the last session, we discussed about, edit logs and file system. How edit logs comes is, let's say I am the client here, and I want to write. Okay, I want to write data. So what this edit log does is that even before something happens on the data nodes, on the data, or even on the file system image, right? It takes a hard copy of the transaction that you want to commit, of the changes you want to commit. Let's say you want to write new data on a new location. Okay, write data on a location, on a location, right? So this particular action needs some metadata to be written, because we want to find the data. The same client can again want to read the data, right? So this edit log is the log that is on the disk of this particular primary node. Okay, this is on this disk of this primary node, because the file system image or the metadata is always on the RAM, right? It's a volatile one, right? If the machine shuts down, or it's acting up, right, we cannot just, like read the metadata, or any client cannot read the metadata. So the disk is more durable storage. So we are writing edit logs on that, right? Now, when we are, restarting the machine, what happens is these two will, like, start, the edit logs will be read sequentially. This is a huge log. Okay, this is event 1, event 2, event 3, event 4, event 5, event 6, like that. So your name node will go through each and every image, and finally it will understand what is the latest, FS image or file system image of your cluster, basically, right? That's how the restarts work. Now, since this is happening, right, the name node will be busy. Right, it cannot serve any of the clients, or it cannot know what is the latest state of the file system, right? So there no block reporting happening, no heartbeat happening. It doesn't know what data nodes are up or what data nodes have the latest data, nothing, no information like that. The restarts are very painful, right? So instead of avoiding this single point of failure here, just one name node here all the time, right? What if we have a standby name node? What if we have a standby name node? That means that if this fails, I can just switch over. I can switch over to new name node, just like how I have done with my data node, right? With minimal lag, so that it would not hurt me with the availability, with the data, staleness, or any data corruption, possible data corruption, right? So that is where secondary name node comes into picture. What secondary name node does is, as soon as some client sends in some request of writing the data or modifying the data or overwriting some data or deleting some data, right? This will be you know like given to our primary name node through our edit logs. That edit log again will be synced to a different machine. Okay, this is a different machine, so that this file system image and this edit logs are stored there safely. Even if your primary name node goes down, I can use this and create a new server, or so that have the fresh copy always running on a secondary name node, so that it can straight up run. It doesn't have to wait till the whole checkpointing thing happens to get the latest file system image. Okay, there is no restart lag, there is no data like stale data corruption, or even data corruption, or even data lag that is happening, because the client can directly communicate to the secondary name node, and then it can mimic the primary name node. The primary this will become the primary name node, and we can have another secondary name node. That is what I have shown here, right? If the name node goes down, now we have the latest fs image because we are writing it to a different place, and we have the edit logs, we have the file system image. The secondary name node will be following very closely with the primary name node with all the edits that are going to happen in the edit logs. So it will sync the both. Since it doesn't bother about the heartbeats, the secondary name node doesn't do any heart beating mechanisms, any block reporting and all of that, right? Only primary name node takes care of all of that, and it updates the all of the updates into a separate server altogether. So this ensures that we are always available, we are always up to the point, and we are, even if in case of failures, be it data nodes or be it name nodes, we are good, right? Any questions here? Reaction, just
So
give a
does
thumbs
this
up.
happen synchronously, the
Yeah,
syncing of grid logs and all?
yep.
Okay.
So the main agenda here is to not let any user feel the lag. As soon as somebody is sending any write request, right, it comes to our primary name node. Any delete requests, any data deletion, writes, any file modifications, that comes to our primary node. As soon as the primary node registers that in the edit log, right, it goes to a secondary name node as well.
Okay. So only after this logs has been written, the actual request is served.
Yep, yep, yep,
Okay.
yep. So
Thank
that
you.
is how we are ensuring that the data is not corrupted. The data is not lagged. Let's say I'm a client, I'm writing a terabyte data, right? Okay. You know, at the last minute, this, operation didn't pass. That means all my primary blocks have gotten the data, and the secondary, secondary blocks that we have discussed the concept here, right? The primary block, secondary blocks. The Hadoop, cluster will, randomly pick one block as a primary block, and then it will update. The replicas of these blocks will again get it later on. Okay. So this mechanism is very important, right? So if the write, while the write is happening and it failed, right? We know for a fact that, the write is happening, and, because we have the log here. If we want to make the name node not as a single point of failure. We need this again on a different machine. Okay, possibly the same machine again, replicated along. So this edit log will be again written to my edit log here on the secondary name node. And since the name secondary name node doesn't like just do block reporting, all of that, metadata information, like entertaining clients and all of that, right? Heartbeat mechanisms, block reporting, checkpointing, all of that. It doesn't do any of this. So that tasks will be offloaded to secondary name node, right? This will be like, following as closely as possible, like, villain, is being chased by our, hero basically. So, right? So that's how, these will be followed very closely, like cat and mouse, all the time, right? So that even if some, issue happens on the primary name node, we are good. Any doubts?
So
Cool.
nearly no lag between.
Yeah. In theory.
Okay.
In
So in
theory.
practical, just a question.
In practice, I will tell you. That's the next thing. I mean, right? So this is how, we are, trying to like, achieve the high availability, right? This is all Hadoop v2, by the way. This is all Hadoop v2 in version 2 of Hadoop. And, version 2 onwards, until now, we are, seeing this basically, right? So now what happens, see, this is all manual because somebody, says that, okay, my name node is not accessible or my cluster is not accessible. Then I have to go and check whether the secondary name node has followed and it has the latest file system image and the edit logs. And then, we will, promote it, right? This is still not very much like automatic, right? It we have to like, go ahead and check the, nodes has failed, data has not corrupted, and, like promote this one, like a secondary name node as a primary name node, right? The whatever the mechanism that I'm, depicting here basically. So this is not basically, not very automatic, right? So what if we could make this automatic, like truly automatic, like, you know, that would mean that we will have more availability. Even if we have like, 40 node failures, including name node and, like including name node and, data node failures, we can keep up, right? Because we don't have to wait for any failures basically. So that is where we will get name node high availability concept. Okay, let's take this for a minute in this picture for a minute. Take in this picture for a minute, and we will discuss what this means, right? I'll explain a couple of, interesting things here that's happening here, and then we will like, go ahead and do details. Okay, since you guys have, seen this, right? Suppose you're playing cricket, right? In or any sport, basically in school or in colleges, as kids. So if you have taken, any like any amount of, seriousness in that game, we would have always quarreled, who gets to bat first and who gets to, bowl first, right? So that's why we invented a something beautiful, thing called as toss. Okay, and then we will elect someone, to bat and bowl. So this is fine. But someone within the team, right, the batting team, will quarrel saying that, okay, I want to bat first. I want to bat first. So who do you give priority, right? So since we are all children, we all have same level of skills. We are assuming, right? So that's where the leader of the group comes in, or the coordinator of the group comes in and says that, okay, I will elect you, the person one, to be the batsman, the first, opener for our team, for our batting team, right? Same thing happens over the bowling team as well, right? Same thing happens with the bowling team. Okay, the bowler 1. This is batsman 1, bat 1. Okay, this is bowl 1. Right? There will be one coordinator who will maintain this. Basically they are called as captains, right? Right? There will be one. Their job is to facilitate the whole thing, to facilitate the whole game going, right? So that is Zookeeper here. Okay, Zookeeper is a standalone service, right? The primary task of Zookeeper is to keep the things going and saying that, okay, you, the person 1 or bowler 1, you are bowling now. Okay, you, right? The umpire who you stand here, and then you get the game going, right? So on a high level, it's also an umpire as well as a coordinator, basically, right? So it decides upon something, and basically makes the whole game going, right? Let's say, how does it work in real world? We talked about like having a secondary name node, right? And we have to painfully go ahead and select the secondary name node and whatnot, right? Now how to do it automatically. So Zookeeper is one such service. Zookeeper is a coordination service. How does that work, right? Suppose you have this name node, right? This is on this is our primary name node. So what happens is that Zookeeper will constantly talk to this particular service through something called as a failover control, that is FC. What is this is basically a session. Session means, suppose you are logged into a particular website like Amazon, right? Every time you log in and you browse, that is called as a session. So Zookeeper will hold a lock on this session for this particular name node. Okay, getting it? So what this lock means, that as long as this session is active with the active name node or the primary name node, we are good, right? We are good. Okay, we are fantastic here. We don't have any issues, right? That means that this node is functioning. This node is getting the block reports, heartbeats, maintaining the replication factors. Everything is happening like clockwork, 24/7. There is no issues with this one, and our clients are happy, and we are serving the data, even though we are having roughly 40 failures, failures per hour. Okay, even though this is going on, we are basically within our SLA or our service level agreement, right? This is basically saying that, okay, even if we have failures, it is our responsibility that you are getting the right data at the right time for the right person. So that's what our SLA is, right? So even though we have 40 failures per hour, roughly 40 failures per 1,000 node cluster, we are still able to serve that. That is what this basically means. Okay. So how does this do, right? In terms of failure, when the name node is not active, it will have some time, like 3 minutes or 1 minute. If our data is very critical, right? 1 minute or 10 seconds or 15 seconds. In the continuous communication between these two, if the name node goes down for a minute, right, and it doesn't respond, the session is basically over. The session is basically over, saying that, okay, now the Zookeeper will delete this lock. Okay, it doesn't consider this as the leader anymore. This doesn't consider this one as a captain anymore, right? It will create a new lock with the standby name node, that this will have a lock. This will create a new lock here with the standby name node. Okay, this standby name node is exactly the same thing as what we discussed as the secondary name node. This is a hot standby. That means whatever that we had, the changes that are approved and like went through in the primary name node, will have the exact same changes, exact same state and stage as we are seeing in the secondary name node as well, right? Same thing going on here as well. Only thing is that the only addition here is that the zookeeper itself is trying to coordinate this process, right? Okay, so what is this? We are seeing some more blocks here, right? This is basically right. Instead of just writing the block reports, heartbeats, and metadata information, and the file system information, right? File system image, only to just and edit logs, right? Only to the secondary name node, as we seen here in the previous example, we are writing to n number of nodes so that we maintain high availability. Instead of one single place, we are writing 3 copies in 3 different nodes. These are separate nodes, just like our data nodes and our name nodes. We are writing it so that even if 2 copies got corrupted in our massive server crash that happened in our system, right? We still have third copy. We can have 5 copies here. It's our heart's content to modify these. It's our heart's content basically, right? you know Again, here the quorum general node, right? These are called as quorum journal nodes. Why quorum? What is quorum? I'll explain, right? So when the write logs are being written here on the journal nodes, the idea here is that at least out of 3 nodes, if we have 3 nodes, at least 2 nodes should say that okay, I have received, 2 nodes should say I have received the edits of the edit log, and I am able to write that in my disk. So that is the quorum is basically agreeing, okay, agreeing that okay, this system basically says that out of 3 nodes I have 2 nodes agreeing that okay, my data, whatever that write log edit log has been written here, has 2 copies that are successfully written. Third one may have it, may not have it. Okay, the idea here is that they will sync between them. Okay, eventually it will get it, but yes, it has to agree to the fact that okay, I write the edit log to my Coral journal nodes only if 2 nodes says that okay, we have received this update, I will go ahead with the next operation, or else I'll retry it. Okay, this is called as quorum. Basically, this is called as a consensus, right? Consensus, right? Saying that okay, whenever I want to write my edit logs, right? If I don't want any downtime, any this one corruption, or any lag, or any misaligned state between the master node and the standby node, right? So I am going to write it to 3 places, and I am going to take the consensus that okay, out of 3 nodes, I have 2 nodes that are saying that okay, this one. So if the third node didn't receive the update at all, what happens is that if the majority of these nodes are saying that okay, this is the latest state of the edit log, so I will take this as an edit log. I will take this as the primary edit log. So that's the reason why we want 3 replicas, and 2 nodes out of the 3 replicas, 3 nodes saying that yes, I have received the update and it's with me. Right? So it's like in saying a class teacher coming into a class and saying that right, you have to write an assignment for me. If out of 10 students, only 2 students agreed that a ma'am has explained that we have to write an assignment today, so it doesn't hold well, right? If 8 people has said that okay, we have to yes, we have to submit an assignment, then yes, everybody will agree to it, even though some people might have not attended the classes, or some people might have just ignored it, right? So that's how this works. So this is all to ensure that we are never seeing any downtime, be it on name node, be it on data nodes, be it on the state of the name nodes as well as data nodes. Any question? Any doubts? I know this is a lot. mean, this is fairly complicated system or even complex system basically. Any doubts? We will stop the recording in a minute. You know, so the one last thing is that you have checked out this particular this one, right? This Google ka server basically. Yeah. Come on, man. Yeah. This thing is called a rack. Okay. This is called as a rack. Basically, servers are stored in a rack. Basically, right? This is called as a rack. If all of the things are working fine and everything is working fine in this rack, and let's say all of the nodes, including data node, name node, everything is present in this one single rack, and the whole rack, power supply got yanked off. Somebody just turned it off without the data center technician or some guy has knocked out the power supply for this particular rack. The whole cluster is gone. The whole cluster will be unreachable. That's why we have something called as rack mechanism, or what's it called, rack aware nodes, something like that. Let me just see this. Yeah, rack awareness, right? So what does this mean? We don't want to store all our nodes, be it name node or this one, be on one single rack. Okay, since they are all connected through network anyway, we will say that okay, I will spread across my nodes on different racks, on different spaces. Even if my data nodes goes down, my name node will be one in one rack. Okay, and my data nodes, even though they have gone, I can just provision this in a different rack altogether. Okay, I can bring this nodes again in different racks. So this is basically our rack awareness, right? Suppose you want to still maintain high availability even after this, right? You can just let's say this is in Hyderabad. Okay, you can just create a new node. Sorry, this whole setup, another node and whole setup again in some place like Mumbai. Okay, even if some flood happened and something happened in Hyderabad and the whole city power supply is gone, we can replicate that in Mumbai again. So yeah, or same place in Hyderabad. Like, let's not take different cities, because the communication, the data communication between these two would be crazy. Like, you'll at least have to spend $1 million per day to just get the data replicated across. Let's say have a location 1 in Hyderabad and location 2 in within the same city. I can just connect with high bandwidth internet between these two, and within this we will have racks, and within this we have Hadoop clusters like this. So this is a high availability design. It's a pattern that we see across in cloud and in high performance computing data center designs and all of that. So I just wanted to discuss this as well. Okay, so in the next session we will discuss about limitations of HDFS. I don't want to stretch this session anymore, because I'll also introduce about S3, how, why we are using S3, or basically any object storage, why we are not using Hadoop based storage systems anymore, right? Hadoop based storage systems anymore. Why we are using object storages, S3, ADLS, or Azure storage, Azure storage, Google file system, Google file system, right? And so on and so forth. All these are all object storages, by the way. If you know about one thing, you can relate to rest all. They have differences. You can relate to them very closely and very easily. So we'll discuss about this. We will discuss about limitations. We will discuss about S3, and we will discuss about a project that I was doing. Like, yesterday I was messing with something on Claude. Luckily, it gave me some this one where I have created a replicated a whole Hadoop like system, not the high availability one, normal one with one name node, two data nodes on my system with this one using Docker. So I'll explain, about this one later on. You can, if you want, if you guys want this, I can share my GitHub link basically where I have uploaded this project and you guys can check this out. All right. This is what you can create Hadoop cluster on your own system, provided that you have resources, and you can basically practice Hive, Hadoop, MapReduce, all of these things on your own system. So this is basically that repository, right? Okay. I'll stop the recording now.